Hey, how are you doing, my fun physics students? This is sort of a continuation of last time. So if you didn't watch the first video, you're probably going to have to watch it to sort of figure out how we got to where we are here. But anyways, here's all the components that we have of circular motion. And so what I want to do is I want to show you how do we get from here to being able to solve for centripetal acceleration. Remember, centripetal acceleration is acceleration toward the center. And we showed how that occurs in circular motion. And now it's not exactly intuitive. You wouldn't realize that the acceleration is continuing toward the center maybe normally, but once you sort of chart it out and you figure out what's going on, you kind of get it, and it starts to make sense. Okay, so here's the change in velocity. So we know that our velocity is going to equal change in position over time. Well, our changes in position are our change from this radius to this radius. So our change in radius over the change in time is going to equal our velocity. We know that the acceleration equals the change in velocity over the change in time. So then that means, and since we showed last time how this angle right here, right, is the same angle, they're going to make the same angles, of course, as this is right here. Because I just took these vectors created up here and transplanted them over here. So then because these are the same angle, what that means is that these lengths, like this length to this length to this length to this length, are also going to be ratios of each other, right? So because it's the same angle between the radius and the velocities, the ratios of the lengths are also similar. Okay, so what does that mean? So that means that the change in the radius over the change in time, which is the velocity, equals the ratio of the change in the velocity over the change in time. So these ratios are equal because these angles are equal, and these triangles that are made from this action are similar. All right, so what we're going to do then is we're going to actually I messed that up real fast. Let me go ahead and back that up. I sort of jumped ahead. So let me just take one little step back real quick. So because the change in the radius, which the angle here between the change in the radius and the change in the velocity angle are the same, that means that the ratio between this radius one and this velocity is the same as well. So the change in the radius, a ratio of the change in the radius to the radius itself, and a change in velocity to the velocity itself, that relates these two triangles. So sorry about that. Now, and I jumped ahead here. Now, if we throw change in time over there, because what we really want to do is get this change in time. If we throw change in time under both of these, it doesn't change the equation because they're both being divided by change in time. Okay, so now what do we do? So that means I'm going to go ahead then and separate out this this length, which is this radius one, and this length here, which is this velocity one, right? So if I do that, I'm going to get 1 over r times the change in the radius over the change in time, right? So that should be parentheses. And that's going to equal 1 over v times the change in velocity over the change in time. So all I did was sort of pull out or take out the radius from the equation in a, so I'm multiplying it back by it here, and so you can see that it's still there. Now we know that a change in the radius over a change in time equals velocity. So then what I'm going to do is I'm going to say, since this whole thing here equals velocity, right, I'm going to sub in velocity right here. And I know that a change in velocity over change in time equals acceleration. So what I'm going to do here, let's get rid of that, is I'm going to say I'm going to sub in acceleration right here. Because what I want to do is I want to get an equation for acceleration that actually works off of these vectors and these angles in the circular motion. So if I just multiply this out, then what I end up here is velocity over radius equals the acceleration over, and this is an average velocity, average acceleration, over the average velocity. So then what I'm going to do is I'm going to say, okay, I'm going to go ahead and this is equals this, so I want to put this into one equation. And so what I'm going to end up with, I'm going to put this into acceleration equals, because that's what I'm looking for is acceleration. So acceleration, and this is actually centripetal acceleration, because this is around the circle. We're using all of this. It's all center-seeking acceleration. I showed you that in the last video. The centripetal acceleration is going to then equal, and so if I bring this v over here, multiply it towards on the other side, I've got v squared over r. So this is your equation for the acceleration of centripetal. Acceleration of centripetal equals the velocity squared divided by the radius. All right, so let's take that one step further. If we go ahead and sort of say, okay, how do we solve for the change in time? How do we get that? So how do we take this equation then and insert time into it? So here's the easiest way to do that. When you think about going around a circle, right? The best way to think about it is in terms of time being what we call a period. Okay? So in physics, a period in circular motion is essentially the time it takes for it to make a complete rotation. Let me go ahead and rewrite that there. So the time it takes to complete a rotation. And so you would actually say that your velocity, your speed or your velocity can be called then the time it takes for a complete rotation. Now you see this in your car engines. You might have a tachometer, and the tachometer says, you know, you're going 4,000 RPMs. So that's telling you that in RPMs is revolutions per minute. So it's telling you that in your you have 4,000 complete rotations in a minute, and so that's your period, right? So or your velocity of your engine, you could say. That's the actual speed of the rotational motion. So your engine is spinning a big thing called a crankshaft, and so you have 4,000 revolutions per minute. If your tachometer in your car says 4, and as you rev the engine faster, it goes up higher, you know, to 5 and 6, and then your engine blows up. So then a period is going to equal then the total time for the circumference. So what is the circumference of a circle? Well, the circumference of a circle, since we're dealing with radiuses, is going to be 2 pi r, right? And let's bring it back to your geometry or something. I don't know, whatever you learn this in, maybe like 5th grade or something, right? So this is pretty easy stuff. So 2 times pi times the radius is going to give me my circumference of the circle, right? So that total circumference of the circle, 2 pi r, divided by the time it takes me to do that, is my velocity, right? So velocity actually equals that. So if we take our equation here and we say, let's go ahead and sub in then what velocity equals in terms of a circle into my equation for acceleration, then we get this. We get acceleration is centripetal is going to equal 2 pi r squared over t, and that's all over r, right? So if I go ahead and simplify this equation, I'm going to square all of this. So I've got 4 square the 2. I've got pi squared and r squared. So pi squared and r squared, and this is over t and then over r. So I can go ahead and cancel out one of these r's down here to get rid of that. So let me just go ahead and do that, and I'm just going to erase it to clean things up here. So I've got 4 pi r over t squared. Sorry, this was also squared because it was up here. So this ends up being squared as well. So 4 pi squared r over t. And so over t squared, sorry, and so that actually equals acceleration of centripetal. So oftentimes, you might be given the total time it takes to make a revolution or whatnot, but this particular equation right here utilizes aspects of the circle and circular rotation and equates velocity as the time it takes to make a complete revolution. And so this would be the equation is substituting that. So these two equations are the same thing. This just takes into account more of the aspects of the circle. So you can use this in a lot of equation or a lot of problems that you're gonna be solving with circular motion. So I'm gonna go ahead and do an example problem in the next video to sort of show you how these things get used in sort of practical problem solving.